Hi, in this video, you will find two different examples on the heat transfer fluxes by radiation of different surfaces. In the first question, I will be talking about a semi-transparent surface, while in the second question, I will be talking about an opaque surface. Enjoy and good luck! Question number one is basically an horizontal semi-transparent plate. This semi-transparent plate we consider it as a general case of any plate. So semi-transparent surface, and given to you the radiosity in 5,000 watt per meter square. So watt per meter square is per unit length, so this is basically flux. Alright, so this is radiosity, flux, and giving to you also alpha, the absorptance is 0.4, and also the problem states that there is certain amount of air is flowing over the top side, or over the top side and the bottom side of this flat plate, with a temperature of 310 Kelvin. Basically this is air flowing over, and H infinity is 50 watt per meter square Kelvin. So if we do, so the problem asked for plate irradiation G, and asked also for emissivity epsilon. Alright, so we will start solving the problem by drawing the energy. First of all, we have to draw the heat flux, the heat fluxes associated in your problem. So we have incident radiation, and we have radiosity J. We don't have to break down J. As I told you before, J can be anything. Leaving the surface, which is given to you here. Any heat flux that is leaving the surface, based on the definition that I have told you before. But here, as long as that we have air flowing over and from the top side of the from both sides of the flat plate, we're also gonna have Q double dash convection, forced convection over a flat plate, right? And if this H wasn't given to you in the problem, you have got to use the, maybe gonna give you the velocity of the air flowing over the flat plate, and you have got to use the flow over flat plate forced convection correlation to get the Reynolds number. You're gonna get Nusselt number, and from here you're gonna get H, and you will be using this H to get the Q of convection, right? So from here we've to do energy balance. So the second thing that you have to do is doing energy balance over the surface. So energy balance is basically energy in is equal to energy out. Energy in here is G, energy out here is Q double dash of convection. The in is G, out is convection, and radiosity plus the radiosity J. Alright, so this is what we're looking for, right? So Q double dash convection is basically H multiplied by Ts minus T infinity plus J. And I forget to tell you that the surface temperature was given to you here in that problem was 360 Kelvin. So it's very simple and very straightforward. Just a direct substitution into that equation. We will have 50 watt per meter square Kelvin. T of the surface is 360 minus 310 plus the radiosity was 5500. We will be left with G as 8000 watt per meter square. So this is the first requirement. For the second requirement is to get the emissivity. So the second requirement is to get the emissivity. So how are we going to get the emissivity here? The second requirement is to get the emissivity epsilon. So the emissivity will only appear from the previous equation that I have right here. J is equal to E plus, as I told you, this is a general case, right? So that plate wasn't an opaque plate. So we have to do J is equal to E emittance, G reflected, and G absorbed. So E, we have this one, we have it as given to you. Epsilon sigma T surface to the power 4 plus G rho plus G tau. And from here I recall the general equation of tau plus alpha plus rho is equal to 1, and rho plus tau is equal 1 minus alpha. So returning back here epsilon, because alpha was the only one giving to you, Ts to the power 4 plus G rho plus tau, and this is gonna be 1 minus alpha Ts to the power 4 plus G 1 minus alpha. And from here, let's substitute. We have alpha, we have G, we have T surface, sigma, epsilon, and we don't know epsilon. We're gonna get epsilon from here. So basically, J was 5500. Epsilon, this is the one we are looking for. Epsilon is found 5.67 multiplied by 10 to the negative 8. T surface 360 to the power 4 plus G was 8000. Again, we got G from the first requirement, 1 minus alpha. Alpha was given to you in the problem as 0.4. And if you solve that problem, this equation, you're gonna get epsilon as 0.74, and that's the first problem. Does anyone have any questions so far till now? All right, was that clear? Hopefully that was clear, right? Good. So the second question I would like to solve today is question number 3. Question number 3. Let's try to solve this question in the last 15 minutes. So question number 3, we have a solar flux incident to a surface was 1000 watt per meter square. Alright, so the surface we have, the problem statement said that the surface we have is that G is coming to the top side, while the other side of the surface is insulated. And the insulation here is going to tell you that there is no transmittance, through the surface. Right, so basically tau is equal to 0, and we deal with that case as an opaque surface, right? So he's asking for, he's giving you, firstly giving to you alpha, which is 0.9, and epsilon, which is 0.2. Right, so alpha and epsilon given to you in the problem. Also, he said that the top side of the plate has air flowing over with a temperature of 25 degrees Celsius and H infinity of 20 watt per meter square Kelvin. So he actually also give you the amount, the heat transfer coefficient directly. But as I told you, I'm gonna write it here. I'm gonna write this note here. Write this note here. If the heat transfer coefficient is not given to you, it's not given, solve the forced convection flat plate external flow. So get Reynolds number, Nusselt number, heat transfer coefficient. Alright, so this is just a separate note. And the requirement is the convection heat flux, also giving to you radiation heat flux, and he asked for the radiation heat flux as well, and he asked for the surface temperature Ts. What's the surface temperature? Alright, so we will start solving this problem by, first thing is draw the heat fluxes on your schematic. So I only draw here G. So also probably we're gonna have Q double dash convection, and we have J radiosity, right? And radiation, as I told you, as I told you before, radiation is included in the beginning here. Radiation heat flux is included in the radiosity, so you don't have to account for it as another outlet from the plate, right? All right. So I will start. We've drawn the heat fluxes. The second thing, energy balance. Energy balance. So for the energy balance here, the energy in is G, energy out is Q double dash radiation plus G. And we're calling J for an opaque surface. We're calling J for an opaque surface because the bottom side of that surface, the bottom side is insulated and tau is equal to 0. So J for an opaque surface was E plus G reflected plus G transmitted.
Sherif?
Yes.
In your energy balance equation, where's the convection? Is it supposed to be there or not?
Sorry, the convection one. This is the convection, that's right. Thank you. And radiation is already included in the J. Yeah, that's right. Thank you. So for here, as I told you, it's an opaque surface, so tau, this term is going to be cancelled out. And J is equal to epsilon sigma T surface to the power 4 plus rho multiplied by G. Okay. So also for an opaque surface, rho plus tau plus alpha is equal to 1. This is 0. Then rho is basically 1 minus alpha. So let's put this here because we don't know rho, we just know alpha, right? So J epsilon sigma Ts to the power 4 plus 1 minus alpha J. Or G, sorry. So from here, we get this and substitute here, right? So G is equal to Q double dash convection plus epsilon sigma Ts to the power 4 plus 1 minus alpha multiplied by G. And let's refine this another one more time. Epsilon sigma Ts to the power 4 plus G minus alpha G. I just multiply G into this bracket, right? So this is going to be cancelled out with this. If we take this to the other side, we will be left with alpha G is equal to Q double dash convection plus sigma epsilon Ts to the power 4. And we are going to refine to substitute the convection by the convection equation. Alpha G is going to be H multiplied by Ts minus T infinity plus epsilon sigma Ts to the power 4. So this equation is only unknown in Ts. So let's solve for Ts first. Alpha was given in that problem was alpha was 0.9, I think. Yeah, alpha was 0.9. Epsilon is 0.2. Alpha was 0.9. G is 1000, which is given also. H is given to you was 20 watt per meter squared. Ts minus T infinity. I just do it here in Kelvin, so the whole temperature in the problem is going to be in Kelvin. Epsilon is 0.2 given to you. Sigma is 5.67 multiplied by 10 to the negative 8. Also multiplied by T surface to the power 4. So if you solve that problem, this equation, you're gonna find out T surface is 339.1 Kelvin, and this is the requirement number 3. And from here we can get Q double dash convection is H Ts minus T infinity. H was 20, Ts 339.1 minus 298 is going to give you a convection heat flux is 838 watt per meter square, and this is the requirement number 1. For requirement number 2, the radiation, for the radiation side. So for requirement number 2 is the radiation. As I told from the definition, Q radiation is equal to J of the opaque surface minus G. So I am not going to do the derivation again. I think I don't have that much time. So J for the opaque surface, or this equation is going to be at the end after refining is going to be epsilon sigma Ts to the power 4 minus alpha G, and this is going to be 0.2 multiplied by sigma 5.67 multiplied by 10 to the negative 8 Ts to the power 4 339.1 all to the power 4 minus alpha 0.9 multiplied by 1000, and at the end you're gonna find that Q double dash radiation is equal to Q double dash convection. And double check that the both numbers are the same, and this is happening because from the definition of the radiation is going to be also the same thing happening with the convection side. Alright, so double check if the both values of radiation and convection are the same. Actually, I didn't write this. And this is radiation. So yeah, I'm done here with that question as well. So does anyone have any question in this last 3 minutes? You guys were clear? Yeah.
Why weren't the two fluxes when they add up, weren't they supposed to add up to G according to our energy balance?
No, in the energy balance you don't have to include the radiation because radiation is is already taken in J, in the radiosity. All right, but we add any other heat that we did not account from the beginning. As I told you before, that J is already in the definition of radiation here. Let's get back here. So the radiation heat flux is the difference between outgoing and incoming radiation. So Q radiation is already into the balance here, so you don't have to account for it. Or if you want to do it all to refine all of them, I think you have to do it this way. I think you have to do it this way. If you have this plate here, so this is G, so we have transmittance, G transmitted, G absorbed, and G reflected, and the emitted as well. And also we have Q convection. Okay, so absorbed, no, so absorbed is taken in here. So absorbed is here. So we're not, is within the control volume, so we're not gonna be including it to, this is G absorbed. All right, so the only ones that you are going to look at all of those all together. If you want to do the to break down, if you want to break down the energy balance, you have to do it this way. If you don't want, so you can take 3 of those and call them J, because the radiation is here based on the surface convection. So you call all of those are J, which is going out with the convection, with the convection flux.
Thank you.
Does that, all right, does that answer your question?
Yes, thank you.
You're welcome. So does anyone else has any question?
Yeah, sure. I have one question. I don't intuitively understand why that Q radiation is equal to Q convection. Is that just a coincidence, or like should they be equaling each other?
They should be equal to each other because first of all, it's an opaque surface, and the second thing is that the heat leaving the surface by radiation is already taken with the convection side already. All right, so because there is a convection from the upper side, and I think this is the case. The radiation leaving the heat, the radiation leaving the surface is already taken by the convection flowing over the surface, and this is what is the solution manual are saying. So I think this does it make more sense. The radiation leaving the surface is taken by the convection.
Yes, that's great. Thank you, Sherif.
Yeah, you're welcome. You're welcome, Spencer. So thank you very much, guys, and take care. I will see you next time in the last break. Thank you again for attending, and I will be posting this as well in Dr. Patel's section.
Thank you. Bye.
All right, bye. Thank you, guys.